We know that the theoretical probability of an event is the ratio of favorable outcomes to all the possible outcomes. So the lead pencil company has a 15% defective rate. So this means that the probability of obtaining a defective pencil is 15%. So if we had 75 defective pencils in our last shipment, how many pencils were in the whole shipment? We can write a proportion here. So 15 out of every 100 are defective. We'll set that equal to 75 were defective. So notice that I have defective in the numerator and total pencils in the denominator. So we want to know how many were in the total shipment. Well, I know that 15 times 5 is 75. So therefore, if I took 100 times 5, I would end up with 500. So therefore, there are 500 pencils in the shipment. We can use theoretical probability, the total number of observations, and proportional reasoning to predict the number of times that an event will occur. So Zeus is running a game booth in which players win a prize if they draw a silver marble from a bag that contains 2 white marbles, 1 silver marble, 2 black marbles, and 3 red marbles. Zeus is expecting the game to be played 40 times. How many winners can Zeus expect? Well, we know that 1 out of 8 of the marbles would be the winning probability. If we set that to what over 40, how many times can we expect there to be winners? So 8 times 5 is 40, so 1 times 5. So we can expect Zeus to have 5 winners. If we spin the spinner 40 times, how many times can we expect the spinner to land on D? Well, the spinner should land on D 1 out of every 4 times, but we are spinning 40 times. So 4 times 10 is 40, so 1 times 10 is 10. We can expect it to land on D 10 times. Will this always happen? No, but this is the expected value. When rolling a standard 6-sided number cube, predict the number of times a 1 will be rolled if you roll 24 times. So a 1 comes up 1 out of 6 times on a 6-sided cube, and we are rolling 24 times. So 6 times 4 is 24. So we would expect 1 times 4, we would expect to roll a 1 4 times. When rolling a standard 6-sided number cube, predict the number of times you will roll at least a 3. So if we roll at least a 3, that concludes that we'd have a 3, a 4, a 5, or a 6. So 4 out of 6 would be the probability of rolling at least a 3. But we're rolling 60 times. So 6 times 10 is 60, so 4 times 10 would be 40. So we can expect to roll a 3, a 4, or a 5, or 6 40 times. The accuracy of experimental results improve when we increase the number of observations in an experiment. Ashley says, pull a tile, look at it, and put it back in the box. You can do that 20 times. Then guess which 9 tiles are in the box. Paul says, I better write these down. So here are Paul's results. So we have color tiles, purple, black, blue, and pink. We tallied and we have a frequency. So the purple ended up being 6 out of 20 times, black 3 out of 20 times, blue 3 out of 20 times, and 8 out of 20 times. So 40%, 15%, 15%, and 30% respectively. If there were only 9 tiles in the box instead of, we can use these percentages to identify how many purple, black, and blue, and pink there should be. So we'll take each percentage and multiply it by the 9 tiles. So we could expect there to be about 2.7 purple, 1.35 black and blue, and 3.6 pink. However, we can't have a portion of a tile, so we'll want to round. So we could say that we think that there are 3 purple, 1 black, 1 blue, and 4 pink. So if I add them all together, we certainly do have the 9 tiles. But the actual tiles are 3 purple, 1 black, 2 blue, and 3 pink. But that's okay. We were very close based on the experimental results that we had. The accuracy, we know, improves with the number of observations that we are experimenting with. So let's look at one of these grabbing games. Let's say we kept track and that there were 204 prizes won when it was played 1,700 times. So that means that we won a prize 204 times out of 1,700, or 12% of the time we won a prize. But let's say it's the busy season and the game is expected to be played 800 times. How many prizes can we expect to be seen? Well, we can take 800 times 12%, and we could expect to give out 96 prizes. The lead pencil company, there are 8,400 pencils in the whole shipment. Mr. Boyd had 59 out of 400 pencils that were defective. Can we determine how many defective pencils were in the whole shipment? So if we had 59 out of 400, that gives us roughly 14.7%, or about 15% when rounded. So if we were to take the defective rate times the number of pencils that we have, we could estimate that there would be 1,260 defective pencils in the shipment. Miss Romero shows her class a bag containing 12 coins and agrees to draw one coin at a time. Show the class and put it back in the bag. The table on the left shows the first 12 observations. The table on the right shows all of the observations the class had done. Which set of data is more likely to help the class guess the amount of money in the bag? Calculate the experimental probabilities for both tables and use them to estimate how much money is in the bag. So on the left, we show the first 12 observations. So there were 3 out of 12 pennies, nickels, 3 out of 12 pennies, 3 out of 12 quarters, and 3 out of 12 dimes. Turning them into percentage, we say that there are 25%. So if we had 12 coins times 25%, we would end up with 3 nickels, 3 pennies, 3 quarters, and 3 dimes, the exact same results that we observed, since there wasn't any variety in our numbers. So if we were to take 3 times 5 cents, we'd get 15 cents. 3 times 3 cents is 3 cents. 3 times 25 cents is 75 cents. And 3 times 10 cents is, 3 times 10 cents. So adding all of them up, we get $1.23. So now let's look at the results if we did on the right-hand side. So we did more pulls from our bag to see what happens. So we have 80 observations. So 6 of the 80, or 8%, were nickels. 13 out of 80, or 16%, were pennies. 34 out of 80, or 43%, were quarters. And 27 out of 80, or 34%, were dimes. So, but we only have 12 coins, so we will multiply each percentage by the only 12 coins in which we have. So 8% of 12 would be 96. 16% of 12 is 1.92. 43% of 12 is 5.16. And 34% of 12 is 4.08. But again, we can't have a portion of a coin, so we'll round them to 1 nickel, 2 pennies, 5 quarters, and 4 dimes. So if I count across, I've got, let's see here, 3, 8, 12 coins all together. And then multiplying them by their respective denomination, we have 5 cents plus 2 cents plus $1.25 plus 40 cents, so $1.72, which is the correct answer. So notice that based on more observations here, we're increasing the accuracy of our estimate by increasing the number of our observations. Possible outcomes for compound events can be listed and counted. Let's use tree diagrams to find the sample space of independent and dependent events. Let's say we need 1 pencil and 1 pen in our pencil case. We have 2 orange pencils, 3 pink, and 2 green pens, and 1 blue pen. What are all the possible outcomes for choosing 1 pencil and 1 pen? So for our pencil choices, we have 3 pink ones and 2 orange ones. Once we pick our pencil, then we have our pen choices. We have 3 pens. We either have 2 green or 1 blue. So for each one we choose, we have 2 green or 1 blue. I see that I have 5 choices for my pencils, 3 choices for my pens. We could multiply them together or count that there are 15 outcomes. Independent events, where one event occurring does not affect another event. So just because I chose a pencil does not depend on what my pen choice would be. So pencil choice does not affect our pen choice. So therefore, these are independent events. We could similarly see that if we chose our pen first and then our pencil, we would still end up with 15 outcomes. This is known as the counting principle. So if there are m ways to do one thing and n ways to do another, then there are m times n ways to do them both. In a variety pack of erasers, there are 1 pink, 1 green, and 2 yellow. Fatima needs 3 erasers in her pencil case. What are all the possible ways she can choose 3 of them? So if we had our first eraser choice, we could have a pink, a green, or 2 different yellows. Then, depending upon what we chose for our first one, our second choice is slightly different. If I chose a pink, I only have a green or 2 yellows to choose from. If I choose a green first, my only options are pink, then yellow or yellow, and so forth. If I choose a third choice, my choices get limited because I'm taking away from what I already had to begin with. These are known as dependent events. One event occurring affects another event. So our first choice affects our second choice because I may not have one of that color left in this particular situation. So we can call this, I had 4 choices for my first event. I took one away, so now I only have 3 choices. And for my third choice, I took another away, so I only have 2 choices. So altogether, I have 24 outcomes. Allie has exactly 4 pairs of socks mixed up in her drawer. They are green, blue, orange, and yellow. If she pulls out 2 socks, what are all the possible different outcomes? And are these independent or dependent? So our first sock, we have 2 green plus 2 blue plus 2 orange plus 2 yellow. So we have 8 choices. Our second, if we took away a sock, now I only have 7 choices in my drawer. So I have 8 socks times 7 socks, so 56 total different outcomes. These are dependent because my first sock choice definitely affects my option for my second choice because I don't have an additional sock in there. Tree diagrams and the counting principle can be used to determine the sample space of more than one independent or dependent event. Let's use a tree diagram to find the sample space of independent and dependent events. Determine the number of possible outcomes for each set of compound events, then order them from least to greatest number of outcomes, pulling 2 marbles out of a bag of 10 without replacing the first marble before pulling out the second. So because these are dependent events, I have 10 marbles that I started with, and then because I didn't put it back, now I only have 9 marbles for my second choice, so a total of 90 choices altogether. Drawing 2 cards out of the deck of 52 without replacing the first card before drawing the second. So I have 52 cards to start with, but then when I take one out, I only now have 51 cards. So total, I have 2,652 options that I would have. Drawing 2 tickets out of a bowl of 20 tickets without replacing the first ticket. So I started with 20 tickets. I took one out and I only have 19 left. So I have 380 options. Notice that the word without replacement is key here. These are all dependent events simply because without replacing, one choice affects the second choice. Take a moment to pause the video and determine if each set of events is independent or dependent. Flipping 3 coins is independent. It doesn't affect the second one. Pulling 2 marbles without replacement. Without replacement is our key that it is dependent. Pulling 2 marbles while replacing. This is independent. We have the same amount of marbles the first time as the second time. Drawing 2 cards from a deck at the same time. This is also dependent. Whether it's the same time or one at a time, we're still having the same amount of cards. Rolling 2 number cubes. Independent. Rolling 1 number cube does not affect the outcome of rolling a second number cube. Spinning 2 spinners that each have 4 equal sections. Again, independent. The one spinner does not affect the second spinner.